All right, hey everybody, welcome back to Physics with Dr. T. In this week's walkthrough, we're going to be looking at vectors and Newton's first law. Now, I brought along with me a basketball, and I'd like to illustrate that at the moment, this basketball is doing a fine job of demonstrating for us Newton's first law. It is an object not in motion, there are forces acting on it, and they are all balanced, leading to no change in motion. And so, while we let this basketball continue demonstrating Newton's first law, let's talk about this week's pre-lab activity. Okay, so for your pre-lab activity, you're going to navigate to the PhET page either through your D2L link or by right-click with while holding Control on the link that's in the pre-lab document, and it'll take you to this location. So you just double click on 2D, and here we are. As you see, much of this information is already mapped out in the pre-lab activity. So let's just kind of quickly go over it. This is over here your display palette, and you see you get sums, you can show values, you can show angles. We're going to turn that off right now. I'm going to leave that to you to decide what you want to show, at least in the short term. And then down here you can display the components in whichever configuration you like, such as in the right triangle configuration as vector components parallel to the axes but at the same starting point. And this area right here projects over to the appropriate axis for the components. Down here you have three vectors, A, B, and C. You cannot use more than three vectors in this simulator. So the trick here is to make your vectors original by changing their lengths and their angle of direction. Down here you can change it over to polar coordinates, but I don't recommend you do that because we want to stick around in the X, Y, Z components, or in this case X and Y components. So we'll click it back here and say ABC. From here you simply grab and drag. I'd start at the beginning, and they're all going to be about the same length, so you just grab and drag it around. You see it kind of jumps to different locations, so I'll just kind of go up right here. Maybe I'll bring B over here and stick it on the tail end of A, on the tip end of A. Grab it and drag it down. Let's be a little bit funky here. I'm just really wanting to exaggerate and use the space up. And then C, now this is where it gets tricky. You are making three vectors that add up to be 0. You're going to confirm this through your calculations after you've printed this out. We are making the equilibrant vector, if you will, but this is not the resultant vector. You are making a third vector that sums the remainder to 0. So you put that in this place like so, and you move it. Now you'll notice as I've been moving those vectors around, if I click on A, it changes and shows you the length or the magnitude, the angle of that vector, the AX and AY. Same thing for B, same thing for C. There's an example in your pre-lab that shows all three vectors highlighted simultaneously. That is a doctored photo. The information is valid. It's just modified, so you won't be able to show all three simultaneously. You'll need to keep this up while you make your notations. You'll need to somehow preserve the values of each of these vectors, at least their component information. So then you come over here and you turn on one of the three types that you like. I'm going to choose this one. You can choose whichever one you like of those three, but I'm just using this one for personal preference. And now I want to move this. So if I move this, say, to right here, if I move this guy maybe to right here, maybe come down a little bit, just a bit. That's kind of messy, so maybe I'll try triangles. Maybe that'll be less messy. Oh, that didn't help. So this is one way you could set them up, and let's see how it looks. Like so. Okay, so that's fine too. But now you can see each vector with its own components showing. Maybe we'll move this up a little bit more just for a little bit more space when you go to print this out. And this is what you're going to print out and put into, so maybe I'll do a print screen. I'll grab print screen and then I'll paste this into Word or into Paint or a Paint program, and then add on the information for the length of each of those components along the X and Y. Make sure you don't get those mixed up. And then that's what you print, and make the calculations according to the information in your pre-lab guide. And that's pretty much it. Okay, so I do want to briefly touch on Newton's three laws because that's going to be up not just for this week, but also for your next lab, which will be studying Newton's second law. So let's just take a quick glance at Newton's three laws as an overview, and we're going to focus on this week's only. So Newton's three laws of motion are Newton's first law, which concentrates on constant velocity, explains forces that are acting on an object that are under constant motion, whether there's zero forces or we have to assess that all forces are acting on it, but they're balanced, much like the basketball earlier in this walkthrough. So, Newton's second law says, okay, under the condition that we're undergoing constant acceleration, what is happening with the force? We'll go into more detail in the next lab. And then the Newton's third law, which is kind of a consequence of the first law, says that when you have two objects interacting, what happens then? And again, we'll get into those at a later point. But for now, I just want to again highlight that under this situation, what you're doing today, you'll be dealing with Newton's first law. X and Y axes, the forces along both directions is zero, sums net to zero, and therefore you have no net motion on your force table, and your ring is perfectly balanced around the pin. Of course, everything that we talked about in terms of vectors could be expanded and used for velocity and acceleration, but right now we're going to talk about this in terms of forces. And what's a little bit less obvious in this particular lab is the fact that the forces are all static. Nothing is moving. Everything is at a static rest. And so dealing with the force as vectors allows us to really explore the vector nature of forces and in general any vector that we're going to run into along the way. So here we have vector definitions and their components as have been talked about in last week's lab and now in this week's lab in great detail. And this seems like it's a very simplified form of what we looked at, but it's really what it boils down to. We have a vector. We can define that vector relative to an existing axis, which I forgot to label, so let me do that. And there we go. We have an x-axis, a y-axis that have been applied here, and along those axes we have components, a sub x and a sub y. Remember, a here is our generic vector indicator. We can replace this with f for forces. We can replace it with acceleration, velocity, displacement. Any one of those vectors, they all have components, and just simply as a simple point, displacement, x and y directions. These are also the hat directions that we talked about, I hat, j hat, or x hat and y hat. If we want the components, it's simply a matter of remembering SOHCAHTOA. These are modified versions of SOHCAHTOA, sine and cosine, where we've eliminated the fraction. So the magnitude of the vector of interest times the cosine of the angle of interest in there, usually referenced relative to the positive x-axis, not always, but usually. Remember that sines and cosines are vary between positive and negative 1, so we expect to see this be scaling down this number from its maximum value to somewhere between positive and negative of that value. So we should never see the components be larger than the actual vector itself. And we can look at this as using vectors to get the components. Now, along the way of doing calculations, you may find that you're going to get down to components. You're basically breaking it apart into the little building blocks of what the vector is along x and y axis. And then you need to go back once you've built up a new vector and compose that main vector from the components. And we can use these expressions here where we have all the x combined into one term and all the y bits combined into one term. And we have ax squared plus ay squared. The square root of all that gives us, this is just a distance formula, folks. This is just the Pythagorean theorem. So keep that in mind. And then this, we did this in lab as a previous statement where the tangent comes from taking the divising ay over ax. So it arises from the components that we already know. Therefore, we're using the components to build the main vector information, the magnitude and direction by knowing those components. This whole lab activity is designed around familiarizing yourself and practicing vector calculations. So make sure if you're weak on vectors, this is what we're trying to focus on, is be able to use these two formulas and use these two formulas intentionally, deliberately, with the goal in mind of I need the components first, or I need to build the new vector based off of knowing what the new components are for a resultant vector. Okay, so now that you've had some experience working with two-dimensional vectors, now let's go ahead and expand our understanding into adding vectors. And the way that we do that is we start with our first vector, vector A, coming from the origins, most natural place to start, and we map it out according to its direction and its magnitude. Then, at the tip of that vector, you start drawing your second vector. And the best way to do that is to sketch in a little XY coordinate that is parallel to the two principal axes. Now, this is the part that I want to make sure that we're very clear about. When you add A and B, you get a resultant vector, a vector that is equivalent to the two of those vectors summed together. That's this red line. Now, that resultant vector would start at the origin and continue to the tip of B. That is your resultant vector. And as you see, I've put the arrow, the tip, at the end of B. Now, that is the mathematical approach. When you're thinking about this in comparison to your strings and forces on the force table, what your third and fourth vector respectively are going to be for part 1 and part 2 are actually your equilibrium vector, where the vector points in the opposite direction of your resultant, because we expect that the resultant vector and the equilibrium vector are equal and opposite and therefore cancel each other out completely, leading to no motion. You're going to be using the component method. The benefit that the component has is that you can add an indefinite number of vectors together and be able to get where you're going, which is to say a resultant vector for the sum of all those vectors. And if we're adding, let's start with just two. If we add two vectors together, well, we write down their components in this way. Now, there may be some confusion about what are these little things that say the little carrots over top of the x and y's. And the answer is this. Each vector goes in a particular direction, and we map them to x and y axes. So to help stay uniform with a vector notation, writing a vector is equal to ax and ay, we need to indicate that the length ax goes in the direction of x hat. And so x hat, y hat, and if you're working in 3 dimensions, z hat, are merely unit vectors, which means that they go exactly in the direction of one of the axes, but their length is 1. So they don't actually change anything. They just let you know the direction of that component. So we write ax in the x hat direction, ay in the y hat direction. Same thing for bx and by. They're both going in the x and y direction. And in order to add these up, we simply need to rearrange the order and get all the x hat direction going all together, all the y hat direction going in the same spot, and then we can group them up. We say ax plus bx in the x hat, and so on. So that we say, well, whatever the resultant vector is from adding these together, in this case c, corresponds to cx in the x hat direction, cy in the y hat direction, where cx is ax plus bx, cy is ay plus by. When you do yours, you'll have 3 vectors added up. You're going to compute a fourth vector, the d vector, using this process, and then you'll again compare that to your force table results and follow the rest of the calculations therein. And so in this lab, you will be working with a force table that looks something like this, and it's on a stand with legs. So this is not detachable, this is just a spare that we have. But I want to direct your attention to properly reading this. Some of the older generations came out printed backwards from what we do now, so this one goes clockwise, increasing in number from 0. We want to pay attention to 0 and going counterclockwise and increasing angle. So make sure that you're careful about reading your force table that way. As you perform this experiment and you get the weights into position and with the amount of mass that you want, your aim is to get this ring to center around this pin in a nice symmetric fashion. You want to be able to pluck at the masses and give it a little bit of motion, and then it'll settle back down into this stable position. So that's the goal. You'll be working with plastic pulleys, and the important thing that I want to highlight for you is that these are plastic and they do not need to be tightened very strong. Just enough to be snug in place, but no tighter than that, otherwise you risk actually breaking the pulley. So make sure that you're gentle with these when you're putting them in place and that you're adjusting them so that we're not damaging the equipment. Everything is plastic. You can adjust the angle of the pulley once you got it in place on the table, so take that into consideration to make sure that your strings are level. Each station is equipped with your force table and 4 sets of slotted weights. These slotted weights should be nicely organized. You can see that there are 10 20-gram pieces, one 50-gram piece at the bottom, one 10-gram piece, and two 5-gram pieces should be in every blue bin. One thing to be careful of when you're working with these are just screwed into place, and so the 50-gram piece can be removed. We don't want to remove it, but it may be loose and can cause you some trouble. So make sure you give it a little twist to make sure it's tightened before you start loading it onto your force table. In case the assembly drops, it doesn't come apart and make a big mess for you. When you're finished, please make sure that you've reassembled all of your hangers and all the masses in the same way, and then store them back in their place. We want to make sure that we have a nice setup for the incoming class, and also to make it easier for us to put these away at the end of this lab week. If your table does not have the slide masses in this way in one of these nice sets of boxes of these nice silver weights, you may find instead that your lab station has a different box altogether, and inside that box is a myriad of masses and weights that have hangers and hooks in this way that look either like this, or there's a blue version of these. And when you use these, you've got a nice variety of masses to go up here, but I do request a couple pair of things. Number one, we want to be very gentle with these because they are breakable. They are plastic, so they're breakable, so we don't want to drop them. So make sure you handle things with care, set things down deliberately and intentionally to make sure that we are getting good care out of them. And you'll find some of your rings with these extra secondary rings here to help allow reducing friction or snagging. So you want to make sure that these remain untangled, but when you go to hang them on there, you just slip that into the notch. It does not need to be completely locked into place. It can just be set into the notch and it's suspended in the way that you need to. And then when you're done, please make sure that you place everything back in here in a nice organized fashion. There is instructions in the box here that tells you how many should be in each slot. It's just more helpful, more respectful to your the folks who come in after you to be able to navigate this. So please make sure you keep this organized as best you can. We do have protractors on hand. If you don't have one of your own, everybody should be pretty familiar with how to use these, so I'm not going to go into detail. I just want to highlight that we have that. Okay, so this is your force table, and as you can see, it's got a round table that has degree markings going all the way around. It's got a ring that's centered on a pin, and there are some other rings and strings. Not every one of them has rings sitting on a ring. Some of them, the strings are directly on the ring. So take that into account when you are making your adjustments. Now, before you begin anything, you want to make sure that your table is level so that you're not introducing a wayward force into your strings that are going across the surface here. And so you can adjust the balance by turning the knobs at the feet and using a level to make sure that it is perfectly level. And to ensure that you have gotten it to a true level, set your level parallel to each of the legs to cover the entire surface of the table and make sure it's ideally flat. So we want to place the pulleys onto the table edge once you've got it balanced. And keep in mind, these are plastic pulleys. They do not need to be super tight in order to be fixed in place. So please be careful and don't over tighten them. But we place them onto the surface in the position that we want. In this case, I want the 0 here. And remember, we have this notch that we're going to align with the markings on the table. Not too tight, just enough for this to sit put. And try and make sure that this pulley is level as you can get it, and you can confirm that when you eyeball it and make sure that it's going straight across from the pulley to the string. So you may have to drop this down just a little bit, but don't let it rest on here. And then the same thing with another randomly selected part for your second vector. So maybe B goes here, not too tight. And then you run your strings over your pulleys like so. And then you estimate the third one. This is another reason why you want to make sure that these are not too tight, is that with it lightly tightened, you can adjust it, loosen and adjust it a little bit easier as you are balancing things out. So we'll put a weight over here on B, and notice it's pulling on the ring. Put a weight over here on the second one. And we're going to adjust that to make sure that they're horizontal. And then take the third one this is light enough. The fourth extra one is light enough that it should not make any difference on your system. So you can adjust the mass once you got it here. This is pointing more towards this way. So either I need to pull more force this way. So we'll give that a bit of a shot. And we see that it kind of jumps around there. So that angle seems to be okay. Let's lower that down, make sure that these are all even equivalent to each other. There we go. And now the question is, do I have too much weight? And you just begin adjusting your weight of your equilibrium mass until you get a good centering of that. So it's still pulling too heavy this way. Take off more. Put this back. Be careful not to drop the weights. And if you do drop the weights, that you're... Now it's too heavy that way. These are 20 grams each, so take some time to adjust. With it there, you can give it a little tap and let it see if it settles. Maybe you need just a millimeter or so, and that looks really center right there. So that we line up that notch with that angle. We're measuring positive angle from 0 in the positive x direction, as it were, all the way around. Okay, so now you and your team have just set up your table for the first set of configuration for part 1, and the question is, where do we want to go with this? Because these vectors things, so I'm not really sure what we're doing with this, and here's what we're going to do. You can see right above my head here the force table, as you might see it looking straight down from the top, where you've got your strings, you've got the pulleys over the corner that the strings go over, and the hanging masters beyond that, past the table, and then you got them. You got the first one at 0. You got the second one at some arbitrary value. Don't use the one I've got here. Create your own. You don't have to go completely crazy. Just don't use 38. And then the third one that I've used to balance it out, I've just picked a number here, folks. So just make sure that if you do get crazy and decide to use something similar to mine, you're not just trying to meet what I've got. I picked a number here. That was a gnat. There's been a fly that's pestering me for a week. So here I have my equilibrium, my balancing force that's going from the ring over the pulley, and the pulley is centered at 152 newtons weighs 152 newtons and is at 201 degrees. So make sure that you're reading your table correctly, especially if you have a table that has 2 tracks of the measurements, because those are measured from different conventions. You want to stick with our usual convention, 0, and increase in this positive counterclockwise direction. If it goes the other way, ignore that track. But your first task is to get all these data onto your first table. So write vector A, give it some reasonable amount of space, distance, length. We want them to kind of be correlated. So I've got this one right around 75 and this one at 105. So I will then do my 105 at, there's 45 degrees. So this is somewhere down 36 degrees. I'll label this. Make sure you label them. It's for your benefit, also for my ability to assess that you are correlating the information correctly. So this is at 38. Make sure you use a straight edge to draw that. I'm doing this freehand. And then your third one, your equilibrium vector, is going to come this way. I'm going to say 201, so that'd be about 200. And 152 newtons, so I'll go a little bit longer. F equilibrium. This is your experimental value. You've adjusted this. Pull the pin out up here. We've pulled the pin out and we've knocked it a little bit to disrupt that motion to see if it's stable. If it's stable, it should rock back into place. If it's unstable, it'll shift one way or another. And then you can readjust this until you get it right. Don't write anything on your pages until you get this balanced. Then you'll take each of these A and B, you'll put those onto your first table in the right spots with the masses that are hanging on them and the angle. You use Newton's first law, the Newton's second law, F equals mg, to calculate what the forces should be, and use that same angle because the force is going the same direction that the mass is causing the acceleration to take place. So you'll notice the notation there, the masses don't have vectors, the forces do show vector notation, and you're writing the magnitude of the force going along A and B. First off, the reason you can't do this, 75 newtons is a huge amount of mass. So, record these onto the table. Then, calculate the force that you've got. So I've got these written up here as forces and angles. You'll write those down actually as masses and angles and calculate the forces from there. And then for this one, record all three of these values. That way you have those all as your experimental results. And then we move on to, now you've drawn this, put this on the table, we move on to the second page to start doing the algebra of adding the components together. Everything for page 2 is about adding up the two vectors that you put in place intentionally, vector A and vector B, and determine what vector C or the equilibrium should be. So the first one we say is 0, and so we put that directly on here. And there's no AY, so there's nothing to draw on this part. But what about FB, force B? Well, in my drawing, number one, you'll notice I've got this light gray x-axis here. That's because that is not the definitive position of the x-axis. Give yourself some space to work here to see the components broken down. So let's say, since I'm in the first quadrant up here, I'm going to want to have this to be further down, so I have all this space for my axis. If you were looking at your second vector over here in the third or fourth quadrants, which is perfectly valid, then you would want to move this up to the top and have all this space down here to do your component work. Since we're in the first quadrant or second quadrant, I'm going to go ahead and mark in my x-axis here for that. So here's our x-axis, and we want this 38 degrees, so I draw it, measured of course, you're going to use a protractor to do this, measure 38 degrees, or whatever your angle is. Draw my 38 degrees, or my angle, whatever it is, mark the location, measure a relative length, we just want to kind of see where this is going, and then sketch out your vector components. Again, this is bx, by. So we're just kind of visualizing what these look like. We're not doing any calculations yet. That comes in just a second. But for now, we just want to see, okay, my x-axis goes this way for my component. My component for my first vector, vector A, goes across from 0, so this is going to be like this. For vector B, it's going to have components on both axes, so I want to draw it in just such a way that we do have components along both axes. So now we've drawn our components, the next step is to go ahead and make actual calculations of our components. And to do that, we'll use these guys right here, just what we saw just over there a few moments ago. And so here now we say for the x component, we'll say so the magnitude here is 75 newtons times cosine of 0 degrees. Make sure you're in degrees, not radians. And then you can put those together, you get a magnitude of 75 degrees. If you do the same thing here for sine, you should get 0 for that part. And you'll do the same basic calculations over here for your, in this part of the thing, not this part. For this part of your table, I don't want to do all the work here for you. You'll do the same thing over here in this part of the table that is blended out. In this case, you'll be able to figure it out from there. And then we want to draw the actual adding of the components in the next field over here. And so now that we have our calculation of the 4 components, we'll come back to this in just a moment. Now let's take a look at what those components look like. We're going to take a look at these magnitudes, but this is where the tip to tail method comes into place. What does tip to tail mean? It means that you draw the tail, you draw it so that the tip of the first vector of the addition is connected to the tail of the next vector. So we start up here at the x, we say, all right, I've got 75 newtons along that direction. And then for the second value, we're going to drop a line right there to pick up where the second one comes off and say, okay, what is my x component from my b vector? whatever that X component is, demonstrate where we go. So this would be your you can label if you want to, but notice these have already been labeled. This is the progress by the X component of A. This is the progress by X component of B. And then what you draw is the net component, which I'm going to do with purple. Okay. The idea being you want to show positive components go to the right, negative components come back to the left. So depending on how you place your vectors, you're going to see different directions of this. And this is why using the second quadrant, the one between after 90 degrees, between 90 and 100, let's say actually between 90 and 270 for your second vector can be a little bit more informative because of the fact that you're going to have a negative component in there, and it'll kind of be a little more instructive that way. So you get to the end of one, the tip of one, and then you drop a line down to put the tail of the next one, and there's your tip to tail process. And then you'll see that when you draw this, you just draw this arrow to wherever the last vector in that pairing goes. Similarly, we apply the same process here for the Y's. Notice for the Y component, we got 0 progress by the A component, so we'll just put a dot there. And then for the second component, not that big, we'll go. And therefore, for this first one, we'll get a net component that goes like so. You don't need to specifically measure these out. I just want you to see how they're being added together. I want you to develop that. This can be a fallback way of doing this, but I want you to see how they're adding together to get that net result, so that when you're checking your math right here, that the spatial intuition is being built in there. Okay? So then we take our resulting components. Well, again, we don't take the resulting components by adding these together. That can be, there's mistakes that can happen in there. Why don't we just add together our X components here and our Y components in this table and put those here? As a result, I get 75 plus another bit. So let's say, well, you know, like 140. I don't know. I'm just picking a number here. You'll add your values up. And then for the Y component, we'll put the value in the Y. That's going to be just whatever the Y's component is contributing in this case. So we'll say, what was that? I don't know. These are now the components of your resultant vector from adding the components together. From here, we use this equation here to, aka Pythagoras. That's why I've got it written here. You show the calculations in the field that's there, and result in this is going to be what's a squared plus b squared. Once we do the calculations, you show the calculation using Pythagorean theorem in place. You'll notice I've put a value in here, 147.05 in my case, and then the calculation, my phone calculator is not doing this, so whatever calculation is, you get out of here. And then you put that in your theta result. This is your resultant vector. What is that actually? This is your resultant vector. What is the resultant vector? This guy right here. If we have our A vector going this way and our B vector going this way, this is the result of adding those together. If you wanted to use some of the other methods you may have heard of, like the parallelogram, you'll notice, let's put A at the end of the tip of B. Now these are parallel, and you see that we are still using, geometrically, we're getting the same result as if we had done it through the component method. So the next step on the last page is to simply go through, convert that resultant vector into the equilibrium vector, and then compare the equilibrium vector to row 3 from your first table, which is the experimental equilibrium vector that you measured on your force table. After you've mastered this first couple pages, the next part of this lab is to repeat this process with just doing the component calculations, and you'll be using 3 starting vectors and then a 4th as your equilibrium vector. So you should be well equipped by that point to be able to manage that, but this is a method you can fall back on some scratch paper if you really need to in order to navigate that very well. Well, that does it for this week's walkthrough. I'd like to remind you that if you have any questions, I'm not just talking about the physics lab. I'm also talking about any homework questions. You're welcome to ask any one of us myself, your TAs, obviously your classmates. And so just a couple quick reminders: make sure that you're pushing chairs back in and you're making sure to clean up all of the weights and getting them back in the blue boxes. This week's lab is, I remind you, a worksheet lab. Make sure you check out the worksheet lab report format and follow it. It should be pretty straightforward at this point for you. And until next time, we'll see you in the laboratory. Never been able to do that before. See you later. Serious face. Hey everybody. Of course, everything about vectors that we're going to be talking about here can be expanded to include distracted. Ooh. Okay. Let's just make sure that we remember to stop recording before we disconnect devices.
Why does every photographer and video maker have one of these?
Because they provide three-dimensional lighting. Trying to meet what I've got. I picked a number here. I've got bugs, man, bugs in here. Friction or snagging. These are some bold flies, I tell you. They just don't care. My x-axis here for that. Fly. Fly. This is all on camera. You want to die on camera, fly? All right. Hi everybody. Welcome to this week's pre-lab activity. Hi everybody. I get that every time. Every week. Every week I say pre-lab activity, not walkthrough. I'm going to collect all these up and I'm going to play for you right now all the interruptions I've had in the last 35 minutes of making this video recording. 38 degrees or whatever your angle is. And then this is the net result of wherever that final fella. These people in their reference. Hello? And have this space down here to draw your components. Geometrically, we get to the same result that we get from, geometrically, we get the same result. Oh my gosh! Stop making noise. People won't let me work. Okay, I'm shooting. Don't you people understand? It's rude. Next week's filming is a lot shorter than this one because the video is already into place. All right, let's do it.
Never thought of it.
Yep, there's a lot that goes into video making.
I will think about that.
Well, that was sloppy. I hope I can make that make more sense in the post. Arises from something else. That's my mustache. It itches. It's in my face. Once you've drawn your angle on the grid on your space, you'll measure the magnitude by measuring the length. And if you scaled, you need to scale back down. And then the angle, which doesn't scale, so you just measure that angle, record those as your resultant quantities in your graphical method table. Next, you're going to use the same configuration and solve it using the trigonometric method. This is a bit more mathematically intense, but again, this allows you an opportunity to compare two different approaches to measuring the vectors that you set up on your force table. The way to do this is that you'll have your two vectors, and this may be upside down compared to what you see in this setup here, but the general configuration is what you want to pay attention to, which is to say the relationship of the angles and legs to each other in order to use these two laws. Here we have vectors A, B, and C, where they have internal angles that may or may not correspond to the actual vector's relative location. A is going along the horizontal x-axis. That's the first vector that we know. Your second vector may be pointing this way, making this an obtuse triangle. It may be pointing this way to make it an acute triangle. Either way, this mathematical method does work, and here's why. The law of cosines here, if you look at it closely, has a part that you might recognize. If we cover up this part right here, now you see we've got a Pythagorean theorem. But Pythagorean theorem only works for a right triangle. So there's a correction that's been added to this to make the law of cosines work for you. And so we imagine that right triangle, this is the correcting term where it takes 2 times the lengths of A and B times the cosine of the angle, this internal angle between A and B. So one of the best steps that you can do for yourself is carefully labeling A, B, and C. You can use different label if that's more comfortable for you, but that's the general idea. And then identify the relative locations inside for your internal angles. Another quirky characteristic of triangles, as useful as they are, there's yet one more. It turns out that the sine of the internal angle divided by the length of the opposite leg is the same ratio no matter which pairing that you look at. So the law of sines will allow you to pick 2 pairings and have one of them be an unknown so that you can solve for that and report that for your internal angle. Once you've performed these 2 steps for your part 1 force table, you'll compare these 2 results using difference of percent error by comparing them to the actual setup on your table. In this situation, our experimental setup is the force table, and we're going to use that as the reference point, and now we're testing these 2 methods against each other using percent error.